Welcome to Chapter 8, Population Change. We'll be looking at human population, but we'll also be looking at ecological populations as well. And what makes them change, how they change. I'm going to slide 3. PD, or the total number of individuals in a given species, which is population density, per unit at a given time. Why do we need to know what a population density is? We talked a little bit, alluded to population densities when we were talking about producer productivity, and we compared a desert with a temperate rainforest, or not temperate rainforest, but temperate deciduous forest, and the number of producers in a given area, that is the density of producers. So when we look at that based on the number of producers in an area, we extrapolated that and we said, well, if there's not very many producers, then it's not going to be able to hold very many consumers either. So when we look at those densities, it can tell us some different things. It can tell us how productive an area is. It can tell us maybe what the limiting factors might be. Might not be vegetation as a limiting factor. Maybe it's water availability for the animals. So we're looking at a scope of different limiting factors for density populations. And also, when we look at density populations, we're also looking at problems that density of populations can cause or create. So, as we move through here, let's just look at these two populations. Let's say these are mice, and we have 20 mice in 100 meters squared, and we want to know how many mice in each meter. We'd simply take 20 and divide it by 100, and that would give us 0.2 mice per meter squared. Well, then look at, we've got 20 mice in 25 meters squared. Take 20, divide it by 25, and that should give you 0.8 mice per meter squared. Now when you look at this, you look at these two boxes, you can tell which one is more dense by looking at this. But if you didn't have a graphic, you would have to do that math. So be able to do just that simple calculation. Growth rate of populations. When we look at global growth rate, we only have to look at two factors. That's birth and death. So as long as births outnumber deaths, we're going to have a positive growth in global population. If at any time deaths would be higher than births, global population would start to decrease. Let's look at the United States. How do we figure out how many people are here and if our population is growing or declining? Well, it's not as simple as births and deaths. I mean, you think about the Earth, you have to be somewhere on the Earth. Nobody's moving to Mars. But if you're in the United States, there's some different factors that affect the United States population. United States population, we still have births minus deaths, but we have people coming in and people leaving that can change our population numbers. So we have to take both birth minus deaths plus immigration minus immigration into consideration. Now, how do you remember which one comes in and which one goes out for immigration? In starts with an I, immigration starting with the I comes in, and immigration starting with an E means to leave or to exit, so E is exit. And how do we calculate this? When we're looking at this, this is per 1,000 people. So if you have a total population, then you're going to have to divide it by that population. You can't just put in birth minus death. You're going to have to put that divided over whatever the population is, or if they tell you to divide it by 1,000, then you'll divide it by 1,000, which will then give you a growth rate. This is a little simplistic. We're going to go over this in class, but you'll get the idea at least. So you have your birth minus death, that quantity, plus immigration rate minus immigration rate, and then what you will do, this will be over 1,000 times 100. So if you put this over 1,000, the birth minus death plus immigration minus immigration, divide that by 1,000, but multiply it by 100. The 100 is going to give you this growth rate in a percent. So if you look at that, you can cross the zeros out of 100 and take 2 of them off, so you're dividing this by 10. And again, we're going to work with this in a class, so I'm just introducing it to you. And we might have already worked on it before you get this. So, maximum population growth, and this is called biotic potential. This is different as far as total population depending on the species. We say that bacteria have a very high biotic potential. That means they will reproduce and go into exponential growth very quickly. And gorillas have a low biotic potential. That's because they don't reproduce very fast, and it takes a long time to grow their populations. And this is just showing bacteria, and here we have data on bacteria. 0 hours, 0.5 hours, and what you're seeing here is bacteria asexually reproduce, binary fission, they're dividing in 2. So first I have 1, then I have 2, then I have 4, then I have 8, I have 16. So every one of them showing every 30 minutes is dividing. Well, let's look at this curve, and we've seen this curve before. This is part of the logistical growth curve in this. So this is for bacteria, number of thousands, and as we see it, it slowly starts to rise, and you follow the numbers over here, and it's plotted. And then when we get to about 9 hours out, which is down here, 262,000, is where we start to, well, actually 8 hours, but 9,000. And then if we go to 10 hours, we're up to 1 million. So very, very rapid growth there. And so we have our initial growth slowly at first, going to about 8 hours, and then it really ramps up in between 9 and 10 hours into that exponential growth. So this is called the J curve, and we'll add a piece to that for logistical growth in just a minute. But first, let's find out what biotic potential, what characteristics each one of these has for high biotic potential or low biotic potential. It has to do a lot with reproductive strategists. K strategists have slow reproductive or biotic potential, and R strategists have high biotic potential. R strategists think of rats, K strategists think of kangaroos. R strategists have high growth rates, small body size, early maturity, short lifespan, large broods, and they give no maternal care, or a little bit of maternal care, basically. Now, an R strategist, or one with high biotic potential, will meet most of these, but sometimes not all of these, such as paternal care. We would classify rats or mice into this, and mice and rats do give paternal care. So they take care of their babies. So let's look at these one by one. Growth rate. That means they reproduce fast and that they have large litters. So, and they mature quickly. So, large broods mature quickly equals a high growth rate. Slow growth rate, later to maturity, so they don't start breeding many times until they're 2, 3, maybe even 4 or 5, and then their lifespan is much longer. I mean, you take an elephant lives for 80 years, and an elephant doesn't start to breed. 4 years is about the youngest, and they don't normally have babies more than once every 3 years, and they spend a lot of time taking care of those babies. So those are case strategists, and kangaroos fit in there as well. I want to go back a minute, sorry. I want to talk about one that fits into both of these a little bit. Think about an alligator. An alligator gives parental care, and it has large body size. But an alligator has large broods. They lay a lot of eggs at one time. They can have 12, 15 little alligators. So, where does it fit? You look at the alligator and look at how many case strategist characteristics they have. They have a large body size. They have a long lifespan. And they give paternal care. Quite a bit of paternal care. So the large brood is the only thing that goes with the R strategists, so they are case strategists. So when you look at these, they're not going to have every one of those characteristics, but they'll have more of one than another. Now let's go to the graph. I've talked about this graph before, so this is just, it's formally in the chapter. And we're looking at paramecium. It doesn't matter what this species is. It can be anything. You're going to have the number on the y-axis will increase, and then time is always on the x-axis. Here's the thing. No matter what species you have that you're dealing with, the graph will look like this. This is called logistical growth. It is an S-shaped graph and takes in the J shape that we had before, but the J shape was still growing and had not reached what we call carrying capacity. Carrying capacity is usually represented by capital K. Carrying capacity is the maximum number that can be maintained by an ecosystem. Maximum number in a population that can be maintained by an ecosystem. So now we're looking at factors that species needs to live there. It could be sunlight. It could be water. It could be food. It could be nesting space. It could be mineral content of the soil. All of those things could be limiting factors that will only allow that number to survive in that ecosystem. If it goes over, those individuals will die back to that number. It can comfortably carry that many individuals. Well, what are we looking at before it gets there? To begin with, we're looking at initial population. And you'll see that the line is fairly straight, kind of like the bacteria line when we looked at that last graph. And then all of a sudden, we get enough breeding pairs over time, and the line starts to increase very rapidly, exponentially. Then you'll notice it has that exponential growth almost straight up, and then before it gets to carrying capacity, it starts to slow down. At that point, there is some push from that limiting factor. If population is growing exponentially, it has not hit the limiting factor yet. There has been nothing causing it to slow down. So it just keeps growing because whatever water, food, space is available, not limited. But as it gets closer to that carrying capacity, we're starting to see some influence from at least one limiting factor. And in environments, there can be many limiting factors. You just have to figure out which one is the most limited sometimes. Carrying capacity can be overshot, and we're going to look at some reindeer on an island. And these reindeer were put on this island. The vegetation was very, very lush there, and so they put some reindeer out there. And here we have beginning populations. And basically what happened, they had good forage, not very hard winters, and so their population numbers just zoomed. Look at this. Really from 1920 is where they started to take off. For the next 20 years, 25 years, or whoops, not for 20 years, whoops, for until right here. They just kept flying up, and their populations over the next 15 years just spiraled because there was so much vegetation. The winters weren't extremely rough, and there are no predators on this island. And then they ran out of grass. So it was a mass death, basically. And in 1950, by 1950 they were almost dead, or died out extinct on the island. No predators. They ate until they just shot past their carrying capacity because so many bred so fast because there was nothing to control the population growth. And they outgrew basically their range. And then they had a bad winter. And many, many died. Just in the next few years, within 15 years. It took 15 years for them to plummet. And within 15 years, there was just about none of them. They couldn't even, once they got down into an area, it was a free fall. And so that's overshooting the carrying capacity. And when that happens and that limiting factor is so stressed and it just doesn't have time to replenish itself. And I think we go to this one. Yeah. This is our last slide, sorry. Our last slide. Survivorship curves. There's 3 different types of curves. There's a type 1, type 2, and type 3. You're a type 1. And basically what that says is that humans do not die very fast when they're young. Most of the death comes as they become older. So that is a type 1. So it just kind of straight line and then a slope down. Opposite of that, think about fish. Fish eggs are, fish lay their eggs externally, and they are not taken care of at all. There's a lot of fish eggs, but you have a lot of atrophy just in fish eggs because they're preyed upon. They're out in the elements. And then the juvenile fish are so small and there's no maternal care, so they're eaten. And so you have high death rate when they're young. But once they get to adult size, you'll see that death rate decline. And those are type 3s. Then you have the type 2s. And notice that a human and a fish, we've got a KNR strategist, and very predominant KNR strategist. So then, look at the type 2. Type 2, they have the same amount of death when they're young as when they're old. And like lizards, snakes, their death rate is constant. So, and birds are also considered a type 2. So multiple births, there's deaths when they're young, there's deaths when they're old, and it just stays throughout their life continual. That's the end of part 1, and stay tuned for part 2.